All right, x86 has a long history with it, which means there's going to be a lot of random information. Hopefully you can glean exactly what you need. So there are different registers, and registers think of as temporary pieces of memory that we can work on. We've already discussed how we make a register, because a 1-bit register is a 1 flip-flop. So a 16-bit register is going to be 16 flip-flops, or in our case 16D flip-flops. And x86 has, x86, I should really say 16-bit x86 has 4 general purpose registers called AX, BX, CX, and DX. Wow, we're original. Then we have pseudo general purpose registers, the stack pointer called SP, the base pointer, the source index, and the destination index. Well, that's kind of weird. But the stack pointer is there to help you grow and shrink the stack. The base pointer is there to help you when you need to jump to the heap. And the strings and destination are for manipulating strings. Then, of course, there's special purpose. The instruction pointer is a register that you should never mess with that says what instruction you are currently executing. And then the E flags are just for general purpose flags, which we've already discussed one of these, which was the compare flag. Was the last compare true or false? That's going to be a flag. There are numerous other flags that are kept in order to make the processor work, but for our intents and purposes, we only care about compare. All right, 16 bits. So the A stands for accumulator. That is how you would do arithmetic, addition plus multiplication. By convention, you use this. By the way, all these are conventions. You can mix them up all you want as long as you're consistent throughout your assembly language, and that is okay. Just any other assembly writer will look at you with ire and probably not want to touch your code. But you are allowed to do it. But please, for this course, stick with this. You'll have fewer headaches. AX is for the accumulator, doing arithmetic. BX is for any type of memory addressing. Welcome back. And then CX, you usually use that when you're using a counter for some type of looping structure. And then D is for data. Now, why do we have the X? Because you don't actually, the X represents all 16 bits. If you wish to represent or access any of the 8 bits, you can call it AH to represent the high 8 bits, or the AL to represent the lower 8 bits. Why would you need that? You might. Modern, well, not quite, well, no, modern extension, E is for 32-bit, so you put an E in front of AX, you now have the 32-bit version of EAX. Same thing with the ESP, the extended stack pointer. And the R was chosen for the 64-bit version. Also, in the 64-bit version, they added 8 more registers because, trust me, the 4 registers are not enough for high-performance computing. They bumped it up to 16, which I would say is a lot better, but you really want 32 in my opinion, but we're sticking with 16 for now. Indianness. This is an issue. Anyone read Gulliver's Travels? Yeah. So you know about the Indianness? Yeah. So I'm trying to remember because it's been a while. But the big Indians always broke their eggs on Lilliput Island. That they broke it on the big end of the egg. The little Indians broke it on the little egg. Well, the little Indians, the king decided that he wanted everyone to break it on the little end, so he ordered the little Indian. Well, the big Indian people didn't want to change, so there was a war, and they had to take refuge on the island of, I don't even know how to pronounce that. Blefishka? Ku? Anyone got that? All right. Yes, this is satire, but we have this. Exactly. And it is really annoying. Memory representation of multiple byte integers. You know, 1 byte integer is from 0 to 255. I mean, that's useful to an extent, but that ends its usefulness pretty quickly. So we need to have a bigger one, like that one. 0A, 0B, 0C, 0D, H, and hex. Well, the question is, which byte is the big byte and which byte is a little byte. The big endian is the highest order byte first, which means that the 0D is the big one. It ends big. Big endian, it ends on the big. The little endian, which is like math, aka the way we actually think about numbers, the littlest one is at the end, the biggest one is at the front, just like our decimal number system. So little endian works just like you think in math. Big endian works in the exact opposite. x86 does little endian, thankfully, but you have to keep this important because network byte order is big endian. That means when you write to the network, by convention, you need to convert from little endian to big endian. Everyone got that? Any questions? Yes.
Why didn't they just make a single standard? Why two?
Well, that's a great question. I do not have the exact answer, but I can tell you what I know. First off, x86 came out first in the late 70s. They're like, why don't we just do it the math way? You know, it's simple, it's intuitive, we're good to go. Then the networks came out, and when networks came out, they were incredibly slow, and they wanted to speed it up. And they noticed that you put a number in big endian, since you're able to receive the size of the number first. I know it looks backwards, but when you're transferring things on the network, it actually will give you the big byte first. You can actually start making some decisions before the other bytes start trickling in, which means that your network card can go faster. Remember that this is back when our computers were a lot slower, so they wanted to optimize network processing because our networks were really slow. Obviously, well, I think that in the long run turned out to be a big issue because we waste a lot of time and power and money doing this conversion from little endian to big endian. And our modern machines, there's going to be basically no performance difference from that optimization. But unfortunately, the network people have agreed on big endian, and x86 has agreed on little endian. Now we have both. Oh well. Or we'll just combine the worst of both. I thought you were the pessimist, right?
I'm trying to improve.
You're trying to improve? Is it working? All right, so big endian, the big is at the end, and then little endian, the little one is at the end. Right, so this may look like the, right, so the big endian, the D's here, little endian that way. All right, great. Operands in x86, this is Intel syntax. Copy content from one register to another, so the content of EBX goes into EAX, or you can tell it to just copy straight up 10 into EAX. You have different memory addressing modes for what's next. For example, if you want to go to address 10 in hex, that's actually address 16, you put solid brackets around it, copy the value located at address 10 hex there, or you can put in a register, which means copy the value pointed to by the register EBX, aka take the contents of EBX, jump to that memory address, grab that information, shove it into EAX. All right, you can actually do some calculations here. EBX plus ECX times 4 plus 10H. This is and this is encoded as an instruction on x86. By the way, if you have a separate instruction for multiplication and addition, do you need to have this? No, you don't. You can do all that separately, have it in a register, and then do it this way. Can anyone take a guess why x86 allows you to do this in an instruction? This is important when it comes to selecting your instructions. Well, if you put in one instruction, that makes fewer instructions, right? Also, by encoding it in here, you're not using another register. x86 has very few registers, so by having a more complex instruction, you're going to have a performance improvement as long as you use that instruction. And by the way, when you go and you look at hardware nowadays, as it has been for decades, they always look for, hey, what's the next best instruction I can put in the processor that'll increase performance and lower power. That's constant. And nowadays, they're going to actually start adding instructions for security as well. So we may get to some of those in this class. But those are newer ones. It's really those three are the big ones that are reasons to add more things to your ISA, which stands for your instruction set architecture. All right, so pointers can be associated. All right, sure. Hey, okay, I like this because it was beautiful pictures. So if you move AL-BL, then it's moving the contents of BL into AL. So if BL had 20H and 20 in hex, which stands for 32, then EAX will now have 32. You could also just move straight up 10 in hex, aka 16, into EAX with that instruction. Or you can do an addressing where you jump to memory address 10H, which is memory address 16. And in this example, it stores 12 in hex, and then take that value and put it into EAX. Or you can jump to where EBX is pointing. In this case, it was 34 in hex, and shove that into EAX. Great. Or you can add two of them, find out what the address of both of them are. Let's see. Huh, that's interesting. Right, find what the sum of both of them are, jump and finally get that value, and then jump over. Because notice EBX pointed to 20, and then it added 02, 2 more to get to 22 hex. Grab that value, shove it into EAX. You will not be implementing this version of move in Verilog. There is no need for extra work because that is just annoying. There are plenty of other instructions. Let's see, exchange. Exchange the values between source and destination. When do you think that's useful? Or what's another word for exchange that you did all the time in data, at least in some of your data structures? It's swap. Swap happens so many times they decide we'll make it one instruction. So now instead of having 3 instructions and using a register, you just have 1 instruction. So for swapping, this basically was more than a 3x speed up for that 1 instruction because you got to relieve registry pressure. Because a lot of times, if you don't have enough registers, you have to take a current register, push it to memory, that's another instruction, do what you need to do with that register, and then pull it back. So that's 2 extra instructions, plus you're using memory, which, as we will find out soon, is an incredibly slow operation. Push stores SRC on the stack. Since the stack pointer is special, the push instruction will automatically shove it on the stack in the right location. It's actually a pseudo instruction, but we'll get to that. Pop will retrieve what you just pushed. And let's see, same as move, but does not do reference. Oh, I misunderstood what LEA stood for. Sorry, guys. What does this do? Move EAX, BAX. So this is same as move, but does not dereference. Oh, okay. So it just actually adds the 2 values. Oh, that's not less than or equal address? Oh well. Push pop manipulates top of the stack. All right, we talked about the stack pointer. In x86, the stack grows downwards. So if you start your stack at hex 10,000, when you push something, it is now, well, now at not hex 10,000, we'll say decimal 10,000. You push something and you're in 32-bit mode, let's say you pushed 4 bytes, you're down to what, 9,996. You push another 4, 9,992. So it keeps growing down. And by convention, this is good. In 32-bit convention, it starts at 0xc and grows down to 0. What's that?
What do you mean by grows down? Like,
So it starts at C000, and then when you put 4 bytes, it would be what? B, F, 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 8.
okay.
So every time you push something, the number shrinks because it's growing down to address 0.
Okay.
And once you hit 0, what happens?
Receiving the stack.
What's that?
Receiving the stack, or you run out of memory.
You run out of memory. The computer explodes. The universe ends. No, you run out of memory.
And then the computer explodes.
And then, oh yeah, then it explodes. Thank you. All right, manipulating top. All right, so yeah, it looks like this ESP is the current stack pointer, and you have pushed 4 numbers on the stack. Great. You push that value. Oh no, you pushed 4 bytes on the stack, which represent a number. You pushed another 32-bit number, which is 4 bytes. That puts these values on the stack, and then you're right there. And then when you pop it, oh, I'm sorry, so that was pushing it. Now when you pop it to EAX, that's specifying you want 32-bit or 4 bytes. So it takes those 4, shoves it back in EAX, and now the pointer's right there. Hey look, it didn't zero it out. It never zeroes it out. Just like in C. Obviously we have addition, subtraction, and or an XOR. Multiply and divide we do have, but there are going to be special situations that we'll have to get to later. We can shift. Ooh, we haven't talked about shifting. We'll have to get to shifting then. But shift, rotate, and XOR, yeah, definitely used a lot in cryptography. All right, I think we've done enough assembly for now. How are we doing? How are we doing?